In this video, I would like to give us some examples of the mean value theorem. So recall the mean value theorem says that if your function is nice, if it's continuous and differentiable on some interval a to b, then there's somewhere where the derivative at a point, which represents your instantaneous rate of change, the slope of your tangent line, will be equal to the overall average rate of change on that interval. So let me give us some examples of this. For the first example, let's consider a function on the interval from, say, 0 to 1. We'll make it a nice function. Let's just make it a function like this. Let's say this is the function f of x equals the square root of x. So then it'll start down here at height 0, and it'll go up here to height 1. Okay, so here's your graph. I guess it's a little more bent, but something kind of like this. So what does the mean value theorem tell us? The mean value theorem says if we calculate this average rate of change, if we calculate this slope from the first point to the last point, this slope m, calculate that, that's going to be f of b minus f of a, so the height is 1 minus 0, 1 minus 0, all over b minus a, 1 minus 0 again. That's just a coincidence that those happen to be the same thing. Comes out to be 1. This average rate of change is 1. Now, the mean value theorem says that there's some point, some special point c, I don't know where it is, there's some point where if you look at the slope of your tangent line, at some point c, that slope of the tangent line should also come out to be the same thing as your average slope m did. That is, the mean value theorem says that somewhere f prime of c should come out to equal 1, because that's the average rate of change. Well, we can actually solve where that point is. We just calculate the derivative. If f of x is x, then we know that f prime of x, the derivative, is equal to, well, this is the same thing as x to the 1/2 power, so the power comes down, so it's 1/2 x to the minus 1/2, which is the same thing as 1 over 2 square roots of x. I just use the power rule on that. And now I can just solve. Plug in c, 1 over 2 square roots of c, ask what does f prime of c equal to 1? Move this to the other side, we get 1 is 2 square roots of c, so the square root of c is 1/2. Squaring, we get that c is 1/4. So there you go. We found here at the point c equals 1/4, the slope of my tangent line is actually equal to my average rate of change. Just like the mean value theorem guaranteed, there would be such a good point because it's a nice function. This function is continuous. The function is differentiable. There are no jumps, so it's continuous. There are no cusp, so it's differentiable. Let's look at a second, more involved example. Let me consider another graph now, and let's make this function a little bit more complicated. How about we do a function like, say, f of x is equal to x cubed. I want to give it some flavor, so let's give it minus 3x squared plus, say, 6x. And I can think about this on some interval. I'm going to think about it on the interval from 0 to 2. From 0 to 2. Okay, at 0, this guy is just 0. It's at height 0. But at 2, if you plug in 2, you get 8 plus 12 is 20. 20 minus 12 takes you back to 8. So at 2, I'm up here at height 8. And it's not obvious what this should look like, but it turns out this graph looks something kind of like this. You can graph this using technology, and you'll get a graph that looks something kind of like this. Okay, what does the mean value theorem tell us? It says you can go ahead and calculate your average rate of change, this m. Let's go ahead and do that. M is f of b minus f of a, so the function at 2 is 8, minus the function at 0 is height 0, divided by b minus a, divided by 2 minus 0. Well, that's just 8 divided by 2, so that's just 4. So this average slope is 4. So the mean value theorem says there should be one point, there's some point here where the tangent line has the same slope. And maybe looking at it, it's not obvious. you kind of try and think like here the slope's too big, but then it starts coming down a little bit. And maybe you can kind of eyeball it and see, yeah, around here there probably is a point where if I try and draw this a little bit better, this tangent line will be parallel to your secant line. The instantaneous rate of change is the same as your average rate of change. Although if you think about it, you look a little bit closer, there's actually, it seems like this graph, because it comes back here again, here it's going to too small of a slope, but eventually it'll increase again to having the same slope. So this graph suggests perhaps there are actually 2 points, 2 solutions, 2 values C for this. You know, some value C1 and then maybe some other value C2. So let's check it algebraically. So that's what the graph suggests. Let's do the math. I want to look at the derivative of this. The derivative of my function here is 3x squared minus 6x plus 6. And I want to set that equal to my slope, which is 4. So I want to say, okay, let's plug in C and think about, is there a solution to 3, that should be a C. Let's call that 3C, that should be a C. Some glare, plug in 3C squared minus 6C plus 6. When does this come out to equal 4? Because that is the value of my average rate of change. When does this instantaneous rate of change equal my average rate of change? Let's try and find those values. So now we just need to solve this quadratic. So we get 3C squared minus 6C plus 2 is 0. So that has solutions by the quadratic formula. C is equal to negative b plus or minus the square root of b squared, which is 36, minus 4ac. So 36 minus 4 times 3 times 2 is 24, all over 2a, which is 6. So what does this give you? 6 divided by 6 is 1. 1 plus or minus. This is going to be the square root of 12. You can pull a 2 out, so that's 2 root 3. So I think that simplifies to something like root 3 over 3. It's the square root of 12 over 6, but I believe that simplifies to root 3 over 3. So here are your values of C. And if you look, maybe it's not obvious that these values are the same as this value. Here's 1 in the middle, and this is saying it's 1 plus a little bit. This is a number that's like 1.7 divided by 3. So this is just a fractions number that's smaller than 1. So 1 minus a little bit, and 1 plus a little bit. Yep, that seems to correspond with the story we have in the graph. So the mean value theorem says as long as your function is nice, this polynomial, that's nice, square root of x, that's nice, on these intervals, these functions are good, they satisfy the condition. So you have at least one solution, at least one place where the slope of your tangent line is the same as your average slope. In some examples, you might have 2 or more places where the slope of your tangent line is equal to your average slope. That's what the mean value theorem is telling you.